Okay, greetings from Monterey, where I am currently at the symposium on naval hydrodynamics, and you guys get a week free from me. So, this is the first of a couple video lectures to cover the Chapter 2 material on fluid statics. In this lecture, we're going to answer some questions about how pressure varies in a fluid, what type of quantity pressure actually is, and how it plays into marine design choices. But first, a few announcements. If you missed my barrage of emails on Sunday, I managed to schedule tutor hours and then find out that some of them won't work. So, the ones that are still in place, there will be tutor hours Tuesdays at 10:30 a.m., but we're not sure where they're going to be held. So I'm still working with Warren and Liam to find a location. So, to be determined on the location. That means that if this lecture is being posted after Tuesday, then there weren't tutor hours. Tuesdays at 6 p.m., it turns out they won't work at all because of a conflict with quarter-deck scheduled events. So the only ones that remain as scheduled, and the first tutor hours for this class will be Thursday, 10:30 a.m. in the Rosenblatt room. So, and that will be with your tutor, Liam McCollum. So, during the last lecture, we covered all aspects of shear and shear stresses in Newtonian fluids. So remember, by definition, a fluid is a medium that deforms continuously under the presence of a shear stress. Or in other words, a fluid cannot sustain any shear stresses without deforming continuously. Viscous stresses are present if there exists a velocity gradient. That is to say, if fluid has a velocity in one direction that's changing in another direction, for example, velocity along the x-axis, or u, that changes in the y direction. That's because particles move relative to one another, and that sliding past one another creates shear stresses between them. For Newtonian fluids in particular, these stresses are linearly related to the velocity gradient. So if I draw that thing that I just erased again, and if we measured the slope of this, then we would find that the shear stress acting on this wall is equal to mu times that slope. Note, the silly person that made this lecture slide wrote the wrong symbol. This is mu, not u. We're doing Greek symbols. So in today's lecture, we're going to cover the case of a quiescent fluid. That is, when the fluid is not moving at all. And when the fluid is not moving at all, then necessarily the velocity gradient goes to zero, because the velocity is everywhere zero. And what happens when the velocity gradient is zero is that all of these shear stress elements in our shear stress tensor go away, leaving us with only these normal stresses, sigma xx, sigma yy, sigma zz. So, one moment. Okay, so as I said, we're going to be talking about pressures, and pressures are the forces, or the force per unit area, exerted by the sigma xx, sigma yy, sigma zz components in the stress tensor. So, if you consider a case where we have a tank of fluid, free surface, and imagine we have a pressure or a point acting here. We'll call that point A. The first thing that we're going to talk about today, and the first question that we're going to ask, is what is pressure really? Is it a scalar? Is it a vector? Or some higher order tensor? That is to say, if we're measuring the pressure at this point A, does it matter which direction in which we point the pressure gauge or whatever instrument we're using to measure the pressure? Does the pressure exert force in a specific direction? Does the direction of the force also carry with it some information about the orientation of the face that it's acting on, as in the case of the stress tensor? Remember, where the element of the stress tensor denotes the face that it acts on, or the orientation that it acts on, and the direction in which it acts. I'll go ahead and give you a gimme here. It is definitely not a higher order tensor. The stress tensor deals with the higher order components of force per unit area. So we're going to address the possibilities of it being a vector or a scalar. And the second thing we're going to talk about is, now if we have, say, pressures at B and C, what is the relationship between pressure at A? Is it greater than, less than, equal to pressure B? And is pressure B greater than, less than, or equal to pressure C? That is to say, that how does the pressure vary within a body of fluid? So we're going to address this second point in the next video lecture, but I just wanted to frame what discussion we're going to be having. So in order to deal with this first question, is pressure, what kind of quantity is pressure, scalar or vector? Let's imagine that we take a tiny little wedge out of the fluid around A. And to save you from my less than stellar artistic skills, the nice folks that made your textbook have already provided us with this sketch. So we're going to call this, the middle of this, our point A. And this wedge has faces oriented with normals to along the z-axis, the negative z-axis. That is this face here, this bottom face. This back face with the normal pointing in the negative y direction. And then these two faces, these two triangular faces with normals along the positive and negative x direction. In addition, there's this blue shaded face with a normal at some angle of theta. Oops. So this is located at an angle theta from the xy plane. So its normal is directed at an angle theta from the z direction. So what we're going to do is assume that this wedge is getting smaller and smaller and smaller to the extent that it becomes essentially a point in space, that is our point A. And we're going to consider the way the forces act on these different faces of the wedge and see whether see how PS compares to PZ, PX, PY. Because these faces are all at different orientations, but as this wedge gets smaller and smaller and smaller, they approach the same point in space. They will tell us whether the pressure is a scalar, that is a single value at that point A, or whether it's a vector, whether it acts in some direction. In the case of it being a scalar, we'd expect to see that all these pressures approach the same value as this volume of this wedge shrinks to zero. If it is in fact a vector, we would expect to see that these pressures are not equal on each of the faces. One moment. Okay, so to tackle this problem, we're going to use good old sum of forces. So we're going to go ahead and evaluate this problem in the y direction and in the z direction only. And let me zoom out a little bit so that you can see. Anyway, so let's begin with the y direction. I know you can't see it, it runs off the extent of the screen there, but here is our y-axis. So we can write Newton's second law, that is F equals ma, as sum of the forces in y equals delta m times acceleration in y. Now what is this delta m? Now this delta m is the mass of the wedge. Remember, delta in this case indicates a very small quantity, and we're assuming this wedge to be extremely small. And delta m is equal to the small volume of the wedge times the density of the fluid, where the small volume of the wedge is equal to 1/2 delta x, delta y, delta z. That is the volume of a triangular prism. So, delta m equals rho over 2 delta x, delta y, delta z. Now, I'd like to call your attention to something. Over in this figure, we'll go ahead and pull up the PowerPoint version of it first. In this figure, you've got these pressures acting on the different faces of the wedge. The one acting on this shaded face is PS, that is the pressure on we're calling this the S face, times delta X times delta S. So this is the pressure at this face acting over the area of this face. Then on the bottom face here, you have PZ, that is the pressure along the constant Z, times delta X, delta Y, that is the pressure, the area of this lower face. And then the pressure acting on this back face, PY, DX, DZ. You get the idea. So these solid lines here, which are forces caused by the pressure, are what we call surface forces. They are pushing or pulling on the surfaces of this wedge. This dashed line here, originating here, is what we call the body force. Now the body force is usually just caused by gravity. It is the weight of the fluid in this wedge. In certain cases, the body force can be caused by things like electromagnetic fields. If it's a ferrofluid, for example, a magnetic field will pull surface elements in some direction or another. And note that the body force in this case is equal to gamma, which we remember is the specific weight, rho g, times delta x, delta y, delta z over 2, which is equal to g, or m, times g. That is simply the weight of the fluid volume. Now, let's ignore the body force for just a moment. We're going to consider some of the forces caused by the surface forces alone. So let me move back to my sketch pad, bring up this figure again. Okay, so some of the forces in the y direction, that is in the horizontal direction on this figure in the upper left. So the force acting in the positive direction, as it's drawn, would be Py times delta x, delta z. Force acting in the negative direction would be Ps, delta x, delta s, times, remember this is the total resultant force acting on this S face. We have to find the component of it acting in the y direction. So this will be times sine theta, equal to rho over 2 delta x, delta y, delta z. Now I'd like to call your attention quickly to something about this expression delta s sine theta. You may notice that if we draw s oops, let's draw this with the right orientation. Y, delta Z, delta S. You may notice that if you look at this drawing, then our innate sense of trigonometry tells us delta Z is equal to delta S sine theta, and delta Y is equal to delta S cosine theta. So let's go ahead and bring this identity over here. So we can rewrite this equation of motion in the y direction as Py delta X delta Z minus PS delta X, and now we just showed that this component is equal to delta Z is equal to rho over 2 delta X delta Y delta Z. One moment while I bring my drawing back up. I'm going to move this over here. Okay. So then we can leverage this to perform some cancellations. It's delta X and delta Z components. Oh, bad me, I forgot the acceleration over here. Remember, MA, not just M. Which leaves us with Py minus PS is equal to rho over 2 delta Y times acceleration in Y. Now remember what I said about we're interested in what happens as this wedge approaches the morphology of a point in space. Which means we're interested in taking the limit of this as delta X, delta Y, delta Z all approach 0. Leaving us with Py minus PS is equal to 0. That is, the pressure acting on this shaded face that's at an angle of theta, and the pressure acting along this face at constant y are equal. Well, this pretty much rules out the possibility that pressure is a vector. Because if it were, unless it's a freak occurrence where we specify some angle theta, these two pressures would not necessarily be the same. But since we never made any assumptions about what this angle theta actually is, then that means Py minus PS equals 0 is valid for any angle theta from 0 degrees through 90 degrees to 180, 270, it doesn't matter. As long as this wedge becomes vanishingly small, that is, in the limit of its size approaching 0, then the pressure at that point will be the same, which means pressure is a scalar quantity. Now, we showed this without even having to deal with the sum of the forces in the z direction, but we're going to go through that process just to be thorough. So, once again, sum of f of z is equal to delta m a z. That is pz delta x delta y is minus ps delta x delta s times this time cosine theta, that is the component of this force acting downward vertically, is equal to rho over 2 delta x delta y delta z AZ. Force equals MA. Once again, make the substitution here equal to delta Y, leaving us with PZ delta X delta Y minus PS delta X delta Y is equal to rho over 2 delta X delta Y delta Z times acceleration in Z. Perform those cancellations, leaving us with PZ minus PS is equal to rho over 2 delta Z A Z. Again, we're interested in the case where this shrinks down to a point in space. So this approaches 0, leaving us with PZ minus PS equals 0, reinforcing our conclusion that the pressure is the same regardless of the orientation at which it is measured. So, that wraps up the topic for this part of the video lecture. In the next installment, we're going to talk about how the pressure at A relates to the pressure at B and the pressure at C. And then we'll start showing how to apply this to calculating the forces on objects that are underwater, holding in water, or floating in water.